Hey guys, in today's video we're going to look at the chain rule. The chain rule is a method of differentiation that we use when we have a composite function that we are asked to differentiate. So for example, if we have a look at this function here, this is a composite function. We have our inner function, x to the power of 4 plus 1, and the outer function is the entire thing cubed. Now we could expand x to the power of 4 plus 1 cubed and then differentiate each term individually, but that would take a little bit of time. And if we change the 3 to, say, 50, it's pretty much impossible to expand x to the power of 4 plus 1 to the power of 50 by hand. So this is where the chain rule comes in. So we use the chain rule to help us differentiate composite functions like this. The chain rule is defined by dy dx, so the derivative function is equal to dy du times du dx. So first of all, we've introduced the term u, and what u is u represents our inner function. So in this case here, our inner function is x to the power of 4 plus 1, and we're going to let that equal u. So u is equal to x to the power of 4 plus 1. And what we're essentially doing here with the chain rule is we're going to be differentiating this function, and that is our du dx. So du dx means that we're differentiating x with respect to u. So over here, we're going to be differentiating x with respect to u. And we're going to multiply that with dy du. So we're going to be differentiating u with respect to y. And where this comes from is we know that f of x is equal to u to the power of 3. We just substitute u into here. And if we let y equal f of x, that means we get y equals u cubed. So differentiating this one with respect to u will give us dy du. So once we find dy du and du dx, we multiply them together, and that's going to give us dy dx. So du dx, differentiating x with respect to u, that gives us 4x cubed, and then dy du, differentiating u with respect to y, gives us 3u squared. So once we have du dx and dy du, then we can say that dy dx is equal to 3u squared multiplied by du dx, which is 4x cubed. And then we can substitute the u back with this x to the power of 4 plus 1, leaving us with dy dx equals 3 multiplied by x to the power of 4 plus 1 squared multiplied by 4x cubed. And then we can simplify the entire thing. Dy dx equals 12x cubed multiplied by x to the power of 4 plus 1 squared. So this is how we use the chain rule to help us differentiate composite functions. Once you get the hang of what's going on here, so once you do more practice questions and you're comfortable converting between u and x, then there's almost a shortcut way of using the chain rule. If we have our function f of x equals x to the power of 4 plus 1 cubed, then to skip this whole defining what u is equal to and all that, what I like to do is I like to pretend in my head that this x to the power of 4 plus 1 is like a box. So if I just literally draw a box, I could have f of x equals this box cubed. So the inside function, just let the inside function be a box. And then when we want to find f dash of x, I'm just going to leave the box as it is for now and just treat this like a normal function. So if I wanted to differentiate this, I bring the 3 to the front, and then I subtract 1 power. So then I end up with 3 multiplied by the box to the power of 3 minus 1, which is 2. And then once I do this step, I have to multiply by the derivative of the box. So this little comma here is another symbol we use for derivative. This is another symbol we use for derivative. So our gradient function is equal to 3 times this box squared multiplied by the derivative of the box. And then once I do that, then I just replace the box back with my original function. So I have 3x to the power of 4 plus 1 squared multiplied by the derivative of this function, which is 4x cubed. And this is exactly the same as this line over here. So we know that our gradient function is 12x cubed multiplied by x to the power of 4 plus 1 squared. So I find this a quicker way of using the chain rule to help me find the derivative. I just pretend that the inner function is a box. I just differentiate this box function as normal, and then at the end I just know I have to multiply by the derivative of what I let the box equal to. But the concept that's happening here is based off what we covered just before, splitting our composite function up into 2 separate functions and then combining them together at the end. So this is a shortcut method, but you do need to understand what's happening with the dy du and du dx. So let's have a look at another question. Differentiate this function and then find the gradient when x equals 1. I'm going to do it both ways. So we're going to do it the way here using y, u, and x, and then we're going to use the shortcut method as well. So this is going to be our dy dx equals dy du multiplied by du dx method. So to start off with, let's rewrite this fraction so that we have a power function. So what I mean by that is, let's rewrite this so that we have y equals 19 multiplied by 2x cubed plus 7 to the power of -1, like that. So once we write it like this, it's a lot easier to find the derivative because we know how to find the derivative with a power function. So our next step is to define u. We can see that this is the inner function, 2x cubed plus 7. So we're going to let u equal 2x cubed plus 7. And then we're going to find du dx. So du dx is equal to 3 times 2 is 6, x to the power of 2. So this is our first derivative, du dx. And then we also know that y is now equal to 19u to the power of -1. I've simply substituted the 2x cubed with u. And then to find dy du, multiply -1 to 19. So we get -19 times u to the power of -2, because we have to subtract 1 from -1. So we have -2. And then this is our dy du here. And then once we have dy du and du dx, then all we need to do is multiply them together. So dy dx is equal to dy du, so -19u to the power of -2 times 6x squared. Dy dx is equal to -19 times 6, which is 114. Sorry, -114 times x squared times u to the power of -2. And then I'm going to substitute the u back with 2x cubed plus 7. So dy dx equals negative 114 times x squared times 2x cubed plus 7 to the power of negative 2. And the power of negative 2 is the same as if we had a fraction with this as the denominator. So we have negative 114x squared all over 2x cubed plus 7 squared. So this is using this method of the chain rule. Now let's have a look at using our shortcut method. So this is what I call the box method. Our box method. So I'm going to let the inner function equal the box. So now we have y equals 19 times the box to the power of negative 1. So dy dx is equal to, just treat the box as one thing. We bring the negative 1 across, so we have negative 19 times the box to the power of a negative 2. And then we need to multiply by the derivative of the box. Once we do this, substitute 2x cubed plus 7 back into our boxes. So now we have dy dx is equal to negative 19 times 2x cubed plus 7 to the power of negative 2 times the derivative of this function, which is 6x squared. And we can see that after this step, it's exactly the same as where we were over here. So we know that dy dx is equal to negative 114x squared over 2x cubed plus 7 squared. Now that we know what dy dx is equal to, we need to find the gradient when x equals 1. So dy dx when x equals 1 is equal to negative 114. 1 squared is just 1, all divided by 2 plus 7, which is 9. 9 squared is 81. So the gradient when x equals 1 is negative 114 over 81. So this is how you use the chain rule. And you can see that the chain rule is very helpful when we have composite functions. And once you familiarize yourself with this method here, using du dx and dy du, then I recommend using the box method because it's a quicker method and saves a lot more time when you're in your exam.